understand a bit more the link between forces, rheology, and deformation patterns. And I'll just talk you through how we've done all that. So the sort of incentive behind the rheology I'm using, the anisotropic plastic rheology, and the experiments we have done come from these lab experiments. And these are being done at Dartmouth College in America with Ellen Schulzen's group. And generally, you take a block of ice, of sea ice, and you squash it in various ways, and you can get these consistent deformation patterns. So these are cracks, and they tend to orientate at this sort of angle due to the crystal structure of sea ice, and you get these orientated cracks. This is a 10 centimetre sample of ice, and sort of schematic of it. So this is and you're squashing it, and what's important is the ratio of these two stresses, which is called the confinement ratio. And what's a consistent result, so on this graph this is confinement, and this is sort of the orientation of cracks, is there's a threshold at 0.3 where you get these orientated cracks, and above that you don't. And these oriented cracks, when you look at sea ice cover, produce diamond-shaped flows, which you quite often see. So this is the incentive behind a rheology that was written by Alex Wilczynski with Danny, and then implemented by Michelle, who's back there, into SICE, which can be used. And going to give you a very quick talk about how it works. So yeah, this is quick. So you've got cracks in sea ice like this. This is a circle, represents an area of sea ice. These cracks can be interpreted as sea ice flows. This is unaligned sea ice. This is an isotropic state. There's no particular orientation. Then, like the crack model with the sample of sea ice, you come up with a stress situation like that, which aligns the sea ice, and then you have aligned cracks and aligned diamonds, and then due to the orientation of these lines and the stresses, so ridging stresses, sliding stresses, and the orientation of this, you can work out the stress-strain relationship. And yeah, so these are line cracks. There's still other cracks going on, but that's sort of the complex sort of arguments of rheology. This is the general incentive behind the anisotropic rheology. I'll quickly then show you some equations, because there are loads of equations involved too, and they're all in this paper if you want to read all the equations. But generally, you take a bit more of a detailed look at this idealized arrangement of diamond-shaped flows or orientated cracks, and this orientation is about 30 degrees between this bit here, so it's 6 degrees total intersection angle is the sole general observed orientation. The sensitivities are done by Michelle for this. And you squash it. But then obviously sea ice isn't always the same, so you also have to do some integration and more integration for co-restriction tensors and stuff like that. And there's a lot of parameterization in this to try and make it work. So you this structure tensor has a distribution of sort of probability distribution of flows, and this is parameterized and put in to change linear alignment when it's aligned. They're sort of all in one direction, and then if it's isotropic, it's just a circle. And then you have to add around the circle all these different stress types. So it's very mathematically complicated. So it's all done in a big, within SICE, a big lookup table. This is all done at the beginning of your model run. Massive lookup table of all these stress types, and the lookup table, you put in your stress strain, you strain, and it will give you out your stress for that particular alignment and everything. And you end up with lots of different shaped yield curves. So Bruno was showing before a elliptical yield curve. This will give you an elliptical yield curve at certain times, and other times it will give you very different shaped yield curves. So that was very quickly the elastic anisotropic plastic rheology. Now I'm going to show you what we've done with it. So here's a pretty animation of some deformation running through SICE using rheology, and I've overlaid some diamonds to show you alignment. So we've used it in the Arctic to simulate. This is a 10-kilometre resolution again. So you can see deformation, there's stress at the bottom and strain at the top. Now, if you look at these deformation patterns going on here, and there's stress patterns, we want to sort of get a bit more analytical about what's going on here, what force is this. So we've taken our setup, this setup of SICE running like this, and then moved on to a square grid. And the previous modelling attempts to do this. So when Alexander Wilczynski was writing the rheology or working on the rheology with Danny, they tried to sort of work out what's going on. So they used a discrete element model that was with Mark Hopkins as well, was helping this part of his model, and they used this with flow aggregates, and they used a particular forcing set on a big square grid to produce these sort of diamond-shaped orientations coming out of these flow-by-flow interactions. and this is all about where the cracks generate, where do they propagate, and that as well. And also, Jenny Hutchings worked on trying to find linear kinematic features using the VP rheology on a square grid, and she used very similar forcing fields to what Alex used, and used the square grid attempts to get these sort of crack and deformation patterns going on here. So we've done something very similar to this using just full size, just getting size and putting it on a square grid and doing some boundary conditions and trying to get some information. So here's the example forcing field. So this is where the analogy between the original square blocks of ice experiments and then using big numerical model is. Because it's a 2,000 kilometre square grid, you can't just squash it from the sides anymore. So what we do is apply a forcing field which has a constant confinement. So it's quite easy here. It's just the major divergence of the wind stress is in the x direction, and then your minor is in the y, and that gives you a confinement, which is this r wind. And these are two example forcing fields. This isn't one forcing field, that would be weird. But this is two example forcing fields. So this is a negative confinement, so your wind is sort of diverging, and this is positive confinement, so converging winds. And this gives pretty much constant stress state on your sea ice over this area, and then we can control the stress state in that sea ice with this forcing field. We've used the same boundary conditions as Jenny Hutchings, and you sort of force a sort of no stress area in this boundary region. Because if you leave it with a closed boundary region, like you enclose it by land, well, the stress transfer of ice is really quick and it flies around, and you end up with it just stay still. Either it's just noise or nothing moves, so you have to be quite clever with your boundary conditions to sort of no stress region here. And then we have a sort of buffer region here, which we don't look at because it's sort of interacting with the no stress. And then in the middle, we're fairly confident we can get some good deformation, which is similar to what you'll get in the centre direction. So this is our box. And because it's a small box, we can test the stability, we can test the resolution. So in general, most of the results are done at 2 kilometre resolution in this box. I've done other resolutions I'll show you in a minute. But this, we've run it, most of the runs are done up to sort of 12 hours with the deformation type, but we've run them up to 10 days. And it's quite consistent deformation patterns. This is the EAP rheology. You get deformation lines pretty quick, and then they sort of look like this. By this point on 10 days, you've got convergence happening here. So this was the divergent wind, so the ice sort of begins to pile up a bit more around here, bridging, and then it gets a bit stronger because it's thicker. So that's happening in 10 days. EVP, so this is straight out the box, this size model. We've tested a bit some of the configurations, like the solvers, the thickness distributions, things like that. But this is kind of consistent results from both of them. And this is the EVP rheology, and so you're getting some lines by 12 hours and 10 days other ones. So it runs for 10 days quite happily, and you can sort of fix it. Then we've tested sort of resolution sensitivity. So at 10 kilometres, it's quite coarse. Yeah, there's quite coarse lines here with the EAP. 2 kilometres of views, you've got identifiable features. So that 500 metres, it's really nice. You've got lovely deformation features here, but yeah, it takes me 48 hours to run a 6-hour model, which is not very efficient. Sorry, because I didn't do very many 500 metre runs. EVP, the way we used it, I did try a lot to try and get the best out of it, and it was still noisy. I'm not sure if it's not reacting to the grid as well, or what's happening, or not quite sure whether the test isn't so kind to it in this situation, but it was getting quite noisy and not quite as many features. At 500 metres, you were getting more coming out, so these sort of high resolution better for it. So this is the sort of patterns you can get. So this is one experiment, and started from the beginning, and it will loop, and then you can sort of get the deformation coming out. And our stress states are fairly constant. It's quite a divergent wind, so other ones are more constant over the region. So you can get these tests, and then we can start changing things and seeing what happens. So this is different confinement. So this one is highly expansive. This is a, right, you got the numbers here, basically see the numbers of the confinement. This is positive, so it's convergent. So these are being pushed in, and these ones are sort of diverging somewhat, so the wind's going out here and in here. What you can see here is 2 different deformation patterns. This is a convergent deformation pattern. This is sort of a divergent compression. pattern, and you're seeing a change along the critical confinement ratio here on this one. So this is one deformation pattern here and one here, but it doesn't happen at 0.3 in the wind. This is 0.3 changing between 0.3 critical confinement ratio in the ice, but it's not the same numbers you get in the wind. So there is a difference going on, and you can see this better if we start taking some lines from these plots. So here we've got a colour code for all these runs I showed before. So blue is sort of divergent, negative R wind, and positive R wind down this way. And so starting from the beginning, they start with isotropic ice, which is important to see later, and slowly some of them align and some of them don't. And this happens for the blue lines are the ones that align, and they have a confinement ratio in the ice which is lower than the critical confinement ratio, and the opposite for the red ones. But what's interesting is that, so this is within the confinement ratio within the ice, and the confinement ratio is less than the critical confinement ratio pretty much for ones where the wind has a negative confinement ratio. So it's just interesting that the applied stress from the wind has a different relationship to the internal stress in the ice. Also, which is nice, you're getting emergent peaks around the critical confinement ratio, which is good because it's written into the model, so you would kind of expect that to come out. What's also interesting is looking at these cumulative density of strain rates, which was what Bruno was talking about before. So we've tested this down and in like taking out individual deformation events pretty much using the square grids, and each one individually is not going straight and going with the supposed power law, but as you add them all together it gets a little bit straighter. Now what we can do is to look a bit more about this. This is uniform sea ice, so the wind doesn't move. It ramps up at the beginning to its slight steady state and then it stays there. And you're getting realignment, but it's going from isotropic to aligned the way it wants to align. So what happens when things start to realign? What happens when the wind starts to move? And so that's what we did next. So we'll talk a bit about this, and we'll go back here to this one. I'm going the other way. And go right, play. Right, so this is the expected alignment you're getting for this run, which is the diamonds going horizontal. So this is the major axis of alignment. I think it's vertical here. The way it's written in the model. So diamonds going vertical, so this is sort of a crap orientation you expect for this wind. So it starts off, they're all pretty much square, they're isotropic. You can't really see it. It happens very quickly. What happens if you pre-align it that way? So it's aligned the way it's meant to be. So when we did the large experiments in the Arctic, you quite often see there was sort of a preferential alignment between wind and flow, but not very strong. But that alignment was there before the wind was. So the stresses were transferring through the ice, aligning the ice before the wind picked up. You didn't see the winds come through and move the ice. You saw the ice move and then the wind would come through. So the stresses transfer faster than the wind systems move, which is expected. So let's pre-align the ice and see how these plots change. So we'll start at the top, which is pre-aligned the way you expected it to be. And everything's aligned, so it's really like tightening up this histogram. And this is very strong now in shear, because when you align the ice in this rheology, it's very strong in shear. And they're all very clustered, and there's less deformation, there's very little high deformation. But the interesting one is when you pre-align it perpendicular. So it's aligned completely the wrong way that it wants to be under that wind situation. And then when it starts, it realigns rapidly. So this is a time series, this first thing, this graph. And it's got a very crazy, so the ones that are going to realign it, so the blue ones, which always can realign the sea ice, is a massive period of readjustments, and they're flipping around. And during that period, you're getting very high strain rates, as the stresses can point all sorts of different angles. As it quickly rotates, it's very weak in shearing for certain situations. We haven't really looked at this very closely, and it's definitely interesting to look at future study, but this is where you can get very high deformation coming from. And if you add all these together and adding realignment, strong realignment, moving winds, then you can start getting the higher ones come out. There's two extra runs here which I can go into depth later, which involve a time series of different winds, where you stack a load of different wind fields together and get a sort of moving one, which is a bit more realistic. At the bottom we've got the EVP. it behaves in very different ways. Generally produces confinements in the stress which are a lot more confined. It likes to be ends up with compressive stress more rather than strong shear alignment. And this is the standard setup with EVP. We haven't gone into much more detail looking at different characteristics of this. We haven't done a lot of rheological sensitivities. There's lots of things you can tweak in these rheologies. So this can be used for different rheologies. And also there are more rheologies out there. These two have been used because we have a size model where we can tweak one, the other, quickly do some experiments. So this framework can be easily set up, I think, to try lots of things. And we can compare all these different runs with graphs like this. It would be really quite interesting. So generally, the confinement's a lot higher. Above this 0.3, there is no emerging critical confinement ratio. Well, it hasn't been told there is one, so it'd be quite amazing if it did pop out with a peak here and a peak there. It'd be quite interesting. And again, there's less. The CDFs in these runs aren't so strong, except for this green one, which is a rotating wind field. So this is realigning winds going on here. This is winds which are moving and changing. The ice is realigning. The ice is having, well, in the EVP it's not realigning, but the deformation, the weakening, everything is realigning. And so this is getting higher deformation patterns coming out when you have a rotating wind field, which sort of says the whole idea of the power law in the Arctic, which has been taken out from observations. That I suspect that's coming out when you take all of the observations. If you took a period with, say, low winds or persistent winds, then you may not get those big realignments, those big deformations, which kind of makes sense, really, if you think about it. So let's look in those two runs. So this was the rotating wind field. It's not a pure rotating wind field because haven't done as little modification to the size model as possible, and it takes 6 hourly winds and interpolates them. So I've rotated the wind field by 45 degrees every 6 hours, and it rotates through them. We've got shifting around. We've got 3 minutes. And another one where you give it a series of winds which start off with a positive confinement, so it's not aligning the ice, then has a negative confinement to align the ice, and then you come back to the original one, and it has a different deformation pattern because the ice is aligned. So it has those parallel lines, the crossed lines, and then another deformation pattern from it being aligned. And you can sort of see a time series of these ones going on here where you have sort of, because the alignment's gone up, this blue line, the relationship between the green line, which is the wind confinement, and the ice confinement, is different with the third wind field, whereas the wind field's the same. So the ice has memory, the Yankee line. Okay, I think I've got through everything. Thank you.
Thank you much, Harry. So we have time for just one quick question, I think. Who's it going to be? Could it be that guy? Yeah, okay. Bruno.
Somewhere in your model, you have a matrix that you look at the lead orientation. So
it's not lead orientation. It's representing the sort of underlying structure of cracks. So this is considering all the cracks in the sea ice, even the ones which aren't leads. So we've got.
How do you weaken? You must be weakening your ice in those preferential direction, and I'm wondering how do you do this in this rheology?
So it realigns when the stress. We don't have a cutoff for the times when the ice aligns. So if we have sea ice, which is under certain stress characteristics, we consider that cracks that are in the ice will become able to actively deform along preferential lines when the stress is in certain characteristics, which is it has a confinement ratio of less than 0.3. And at that point, we then can say, right, there's cracks all through the ice. Some of those cracks matter in deformation, some of those cracks don't. So particularly if you want to shear the ice, then cracks which are along the shear line are going to work towards that shear stress. A crack which is, say, perpendicular is not going to matter to that stress. So then we're going to say if the stress state is such that that crack is going to matter, then we align the structure tensor to consider those cracks in that alignment are important. That has a time scale to it, which is, there have been sensitivities done to that, and that has a time scale which decays the your structure tensor, which represents which cracks you are using, towards its aligned state. So we've done work which takes the structure tensor from an aligned state back to an isotropic state due to thermodynamics. You can sort of make assumption for that from the growth of ice and stuff to bring it back. It's been difficult to find timescales to really show how long it would take to go the other way. If you look at timescale of crack propagation for a flow, been some studies, but not lots. It's just really quick, really, really fast. So we can say order of 4 or 5 hours to say over a grid cell that will become aligned. So it's difficult. So it's not necessarily a damage function. It's more of a time scale of if the stress is in the right configuration. It's been difficult to say if there's a threshold for that stress either. So yeah, these are all the questions within rheology which need to be narrowed down. Yeah, hope that makes it a bit clearer.
Okay, thank you much, Ray. We're going to have our next speaker now.